I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on magnetism, magnets, magnetic fields, and how to calculate magnetic fields from a current carrying wire. In this series of videos, we're going to talk about magnetism, properties of magnets, magnetic fields, and electromagnetism. In this video, we're going to talk about magnets, magnetic fields, and specifically magnetic fields from current carrying wires. So let's talk about magnets and their field lines. So let's start with a simple bar magnet. A bar magnet has a north and a south pole. So this is called a magnetic dipole, much like two charges, like a electric dipole, where we have a positive and negative charge. If we draw those field lines coming from the magnet, the field lines come out of the north pole and into the south pole, much like a electric dipole. So a magnetic dipole has a north and south pole where the field lines point, as we see. Now, there has not been discovered a magnetic monopole where we have just a north or a south. If you break that magnet in half, what you get is two equally strong magnets. It just repolarizes itself, or the one side's north and the other side is south. So you end up with two equally as strong magnets if you break the magnet in half. So a magnetic monopole has not been discovered as of yet. Let's talk about the magnetic field lines of the Earth. So we'll start by looking at the globe. And we know that the globe has a geographic north and south pole, the north pole being in North Canada and the south pole being in Antarctica. Now, a magnetic south and north pole are actually going to be aligned like this with the bar magnet that we see. Now, the Earth's magnetic field is actually aligned opposite of the geographic poles. So what causes the magnetic field around the Earth is the flow of molten iron in the core of the Earth. That molten iron flowing causes the magnetic field. It aligns with the magnetic south pointing towards the geographic north pole and vice versa, with the north pointing to the geographic south pole. So that means that the field lines are going to be oriented pointing out of the north pole of that magnet and towards the south pole. So if we have the magnetic axis, we see that the magnetic south pole is actually at the geographic north pole, and vice versa. The magnetic north pole is at the geographic south pole. And the poles are off just by a little bit, maybe about 17 degrees. It's going to vary because of the flow of the molten iron in the core. So if we take a compass, which the needle is a magnet, and we get that to align, we know that it's going to point towards the north. Well, the red of the compass is north and the white of the compass is south, so it aligns so that the north points to the magnetic south pole, as you would see as you were traveling outside. If you had a compass, it always points towards the north pole because it's attracted to the geographic south pole. So because we have magnetic fields, we're going to have things in 3 dimensions. So if we have vectors pointing up, down, left, or right, that's 2 dimensions. We're going to need a 3rd dimension with things being directed into and out of the page, so perpendicular to the page. So the notation we're going to use to direct something out of the page is going to be a dot. So that's standard notation to show that either current or force or something's pointing out of the page. And directed into the page is going to be an X. Now, for most situations, you're going to be told that it's a field or something pointing into or out of the page. But if it doesn't, we could think of an arrow being shot. As that arrow approaches you, it looks like a dot. So the dot represents an arrow coming out of the page. If the arrow goes into the page, we see that X of the feathers of the arrow flying away from us. So that's a good way to remember directed into the page or out of the page. The dot as an arrow coming towards you and X as it's moving away from you. So we're going to talk about magnetic field of a current carrying wire. So this was discovered by a Danish scientist, Hans Ørsted, in 1819. He actually set up an experiment that he was showing in his class for an electrical circuit, and he accidentally left a compass laying nearby a wire. And when he had the current flowing through the wire, he noticed that the compass deflected, and as he turned it off, it went back to its normal position. So this was very interesting to him, so he experimented and found that a current carrying wire actually produces a magnetic field. Let's look at a simple version of what Hans Ørsted discovered. So we have a wire, and that's directed out of the page, and we're going to place a compass near that wire. And the wire currently is not carrying any current. So if we turn the power source on, and now we have current flowing through that wire coming out of the page, we can see that the compass gets deflected, and the North Pole points actually towards the west. Now if we turn the current carrying wire off and we align 4 separate compasses around that wire, and then we're going to turn the wire back on so it's carrying current, we're going to see how the compasses deflect. And we'll see that the top one still deflects to the west, the one on the left points south, the one at the bottom points to the east, and the one on the right didn't deflect at all. So what we can see is that we have a counterclockwise magnetic field around that current carrying wire. So we're going to figure out how to represent the magnetic field from a current carrying wire. So let's start with the wire in parallel to the plane of the page. And in that wire, we're going to have positive current flowing from left to right. Remember, direction of positive current is the conventional current. So current's going to be flowing to the right along the page. And what we're going to use to find the direction of the magnetic field is the right-hand rule. So you point your thumb in the direction that the current is pointing, and then you curve your fingers around the wire to show the direction of the magnetic field, as you see on the screen. So our thumb's pointing to the right, and we can see that we curve our fingers around the wire to show the direction of the magnetic field. So as we curve our fingers, we see that on the bottom side, it goes into the page. On the top side, it comes out of the page. When it's behind the wire, the magnetic field is up, and when it's in front of the wire, the magnetic field is directed downward. Now, to represent it like this would be kind of confusing to be able to understand the notation, so we're only going to look at the direction of the magnetic field in 2 dimensions. So we have the wire that has current flowing to the right. Then we're going to represent the magnetic field coming out of the page with dots at the top and into the page with X's on the bottom. What we're going to do now is we're going to learn how to calculate the magnetic field, or the strength of that magnetic field, which is represented by a capital B. And we're going to look at proportionalities first. So first we're going to look at current. When current increases, we can see that the strength of the magnetic field gets stronger, which gives us a direct relationship between magnetic field and current. And if we go back to our original situation and we look at a distance that's further from the wire, we can see that the magnetic field strength decreases. So that means that the magnetic field strength is an inverse relationship with the distance from that current carrying wire. Now, we also know that we can take any proportionality and make it an equality by multiplying by a constant. And we're going to multiply by mu naught divided by 2 pi. And this is going to give us our equation for magnetic field. B equals mu naught I divided by 2 pi r, where B is the magnetic field strength measured in Tesla, which is abbreviated with a capital T. And we need to note that magnetic field is a vector quantity, so we're going to have to do vector addition to be able to find the overall magnetic field if we have multiple sources. We also know that I is the current in the wire, and that's measured in amps. R is the distance from that wire, and that's going to be measured in meters. And mu naught, our constant, is going to be the magnetic permeability of free space. And that value is 4 pi times 10 to the negative 7th Tesla meters per amp. Now note, in the denominator we have 2 pi r, which is the circumference, which is basically like the distance around the path for the magnetic field. Let's look at an example problem. So we have sections of 2 parallel wires that are shown, and they're separated by a distance of 5 centimeters between the 2 wires. And the current in the left wire is 1 ampere, and the current in the right wire is 2 amperes, and both currents are directed upward in the plane of the page. And the question is to find the direction and the magnitude of the net magnetic field halfway between the 2 wires. So what we need to do first is to figure out the direction. We're going to use the right-hand rule to figure out the direction on the left. We can see that our fingers, as we point our thumb in the direction of the current, would point into the page, so we'll represent those with X's. Then we'll find the direction of the magnetic field on the right wire using the right-hand rule, and we can see that our fingers wrapping around the wire would point out of the page, coming out towards us from the right wire. So we've got one of them that is directed into the page from the left wire, and then the magnetic field directed out of the page from the right wire. And what that tells us is that since they're pointed in opposite directions, they're pointed parallel to each other. So all we'd have to do to find the vector sum of those two magnetic fields is simply just subtract the values, since they are parallel, or also known as anti-parallel, since they're pointing in opposite directions. So let's go ahead and calculate the magnetic field. We'll represent the left wire as B1 and the right wire as B2, since those were I1 and I2. So we can go ahead and calculate the magnetic field for B1, which we substitute in the values, 4 pi times 10 to the negative 7th Tesla meter per amp, 1 amp here, and 0.025 meters, because it's halfway between, and 2.5 centimeters would be halfway between. So 0.025 meters. You can see how the units cancel out, leaving us with just Tesla as the unit. And that's going to give us a magnetic field of 1.6 times 10 to the negative 5th Tesla produced by the left wire. The right wire, we can go ahead and change the current to 2 amperes. The distance is going to be the same because it's the midway point between the two wires. So we cancel out our units and get 3.2 times 10 to the negative 5th Tesla for the right wire. So B1 is 1.6 times 10 to the negative 5th Tesla pointing into the page, and B2 is 3.2 times 10 to the negative 5th Tesla pointing out of the page. So the B2 is going to be bigger from the right wire. So to find the total, we're going to subtract those two values, which is going to give us 1.6 times 10 to the negative 5th Tesla is the total magnetic field. And because the outward directed magnetic field is stronger, it's going to be directed out of the page. So that is the total value of the magnetic field produced by the two current carrying wires midway between the two wires. So this is an introduction to magnetic fields from current carrying wires. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X @CabbyCoaches.